Thank you for the opportunity to talk to you about water-soluble cannabis extract nanoemulsions. I'm going to discuss their benefits, their properties, their composition. I'm going to talk about ways to characterize them, and at the end I'm going to tell you how anyone can make their own without being a scientist or an engineer. There are several traditional ways of administering cannabis that everyone knows about. Oral, which is where you consume it as an edible or an oil capsule. Pulmonary is vaping, smoking, dabbing. Transmucosal is sublingual or intranasal or even rectal exists, right? And transdermal is when you deliver it into the bloodstream through your skin. Not to be confused with topical, which is for skin condition treatment, right? Now, each one of these methods has advantages and disadvantages. And very quickly going through them, is oral is discreet and convenient, but it's very slow, inefficient, unpredictable, the bioavailability is low, and you don't really know when things are going to hit you, right? Depending on who you are, whether you ate or not, it's very finicky, inconvenient. Pulmonary, not everybody likes to use their lungs, right? Lungs are not meant for bringing things into your body other than oxygen. So checks and balances that your small intestine and digestive system has are not really there for the lungs. So it's harsh, potentially harmful. Transmucosal works faster, but not all types of transmucosal delivery are actually are what they seem. For example, sublingual is very frequently transferred into digestive because you think that something's under your tongue, but really it's being washed down by saliva. So it's not always what it seems. They're also not very discreet, especially intranasal, I guess, not very social. I guess rectal delivery would be the last on my list of social activities, right? And then transdermal is slow and quite inefficient. So the question is, why are all these methods around? Why are they coexisting? Why isn't there a clear winner? For example, if you look at the alcohol industry, and I'm guessing this is going to be a recurring theme in this conference, that making parallels with the alcohol industry is very appropriate at this point. So in the alcohol industry, I mean, you could vape ethanol if you wanted to. You could figure out how to make an edible out of it, probably. You could put it on your tongue. You could make a patch with it, but why would you? You could just have a drink. And the reason that that's what everyone does is because a drink with ethanol works quickly, predictably, reliably. The bioavailability is high. The onset of action is short, right? And that is because ethanol is water-soluble, unlike cannabis. So the question is, if you could make cannabis extracts water-soluble, you would make beverages out of that. Wouldn't that just be a clear winner? Well, the argument I'd like to make is that, yes, this is, I think, where we're all going. And clearly, at this point, everyone knows that you can do that. This is what a nanoemulsion looks like in a liquid on the right, and solid form as a powder. So you could just, these are some nanoemulsions that we make. They can go into water. You give it a quick stir. They disappear. It's completely clear. The dose is known. The action is predictable. The bioavailability is high, and I will explain why. And this can go into pretty much any beverage that has water in it. Before we get into the composition of nanoemulsions, what exactly are they? We need to quickly talk about what a surfactant is. It's going to be the only kind of sciencey thing here, and I'm not going to get too deep into it. But the point is that if you take a water-soluble molecule and fuse it to an oil-soluble molecule, so in this case, you have this entity in the circle that's a part of the molecule that would dissolve in water. The tail end, the oil-soluble part, that's just a fatty acid tail. So the head likes to dissolve in water, but not the oil. The tail is exactly the opposite. Likes to dissolve in oil, not in water. We're going to label it like this schematically. And then if you have an oil and water mixed together, obviously, no matter how vigorously you mix oil and water together, once you stop doing that, they will separate into layers, because water likes other water molecules, oil likes other oil molecules, and so they kind of hang out with their own, and oil is lighter than water, and so it just flows to the top. If you put surfactants into this thing, then they will arrange themselves spontaneously this way, with the heads into the water and with the tails into the oil. And the point is that once you look at this situation from the water's perspective, you see friendly tails, something that likes to dissolve in water. So water is happy. You look from the oil's perspective, it's oil-compatible tails. So suddenly the hostility is gone. They get along better, if you will. So once you have this capability to relax this interface, to make the situation more compatible, you can now start making oils compatible with water. In this industry, it's typical to say that oils become water-soluble. Very technically speaking, they're not soluble, but they behave as if they were. And I will show you that for all intents and purposes, what they become is good enough to make beverages. They become close to being true solutions, even if they're technically not. And so this is what a nanoemulsion is. It will comprise a carrier oil. That's most of the interior, the yellow interior in the droplets. And that's typically a triglyceride. We recommend long-chain triglycerides. They help absorption better than MCTs, for example, medium-chain triglycerides. There will be your bioactive. That could be CBD, THC, or it could be a completely different thing. It doesn't have to be a cannabis extract. As long as an oil-compatible bioactive, it will go inside the interior of the drops. There will be a surfactant. So surfactant is, you recognize it, it's on the surface. The tails are pointing towards the water. The heads are pointing towards the water. The tails are inside the oil. So the interface is more compatible. Then water forms the outside, but if it's a powder, then that blue stuff, that's water for a liquid, it doesn't have to be water. It could be something like water, for example, a type of sugar, where the continuous phase has the properties similar to water, but happens to be solid at room temperature, which means you can make a powder out of it. Once you put that powder into water, that continuous phase dissolves out into the water. Water takes its place, and now you have a liquid nanoemulsion. So you can make a beverage using a powder, or make let's say a tablet, put in your mouth, and it will dissolve in your saliva, and you swallow it as a beverage. I guess a saliva beverage, if you will. Typically, there are some preservatives. It's optional, and the types of preservatives are up to you. This doesn't interfere with the nanoemulsion itself. It's only for the beverage to be what you want it to be, so that's typically up to the manufacturer. And importantly, for this thing to be a nanoemulsion, the median of the droplet size distribution, it's called D50, should be below 300, 250 nanometers or so. Technically, anything that's under 1,000 nanometers could be called a nanoemulsion, but on the upper end of this range, these systems don't really behave like nanoemulsions. They separate, they don't have long-term stability, they don't increase the bioavailability. So for the intents and purposes of what we are trying to do here, the median droplet size should really be around 250 or below. Now, if the D50 is well under 100 nanometers, or rather the entire droplet size distribution, all droplets in your system are under 100 nanometers, this type of nanoemulsion will become translucent because the light doesn't interfere with obstacles that are smaller than 100 nanometers, really. So the light travels right through it, and you can see through this type of system. The advantage of those systems is you don't really, unless you need the actual number, you don't really need droplet size measurement capabilities to know that your product is still good, because if it's not good, it'll become cloudy. And if it's not cloudy, that means the droplets are still small, right? And ideally, the median of the droplet size distribution should be about 20 to 40 nanometers. There's a good reason for it, and I'll get to it soon. This is what typical droplet size distributions look like for a liquid and a solid nanoemulsion. So on the left, you have a 20 milligrams per milliliter CBD nanoemulsion. These are just samples that we made. The D50 is about 26 nanometers in this one. And on the right, it's a powder. This is our premium powder. The droplet size distribution is all under 100, so it becomes completely transparent when you dose it into water. And the D50 is about 35 nanometers in this one. Now, every once in a while it comes up that people are concerned about nanotechnology potentially being something dangerous. And this deserves a couple of minutes because the word nanotechnology could be scary. In Europe, for some reason, people are really scared of the word. But that doesn't mean that nanotechnology itself is new or scary. So some novel nanoparticles, carbon nanotubes, and metal oxides definitely require some scrutiny because they didn't exist before, and who knows what they do to you. But that doesn't mean that just because there are some small droplets that this is potentially a dangerous thing. Specifically, English breakfast tea is a nanoemulsion with droplet sizes averaging about 25 nanometers, so very similar to a good nanoemulsion. Coffee is a nanoemulsion, beer, milk, your blood, your gastric fluids. In fact, if it weren't for small droplets, you couldn't digest oils because, and I'll get to it in the next slide, I think. When you digest any type of oil or fat, it becomes something called mixed micelles temporarily in your small intestine, and those are nanoparticles, and that's the only way they're going to get absorbed. So just because something has nanometer-sized particles doesn't automatically make it dangerous. Now let's talk about how things get absorbed. This is my other sciencey slide, and it'll be the last one. But it's important to understand why this works. Why nanoemulsions? Why do they improve the bioavailability? Why is it faster when you do it that way? And why specifically that size? Because if you understand why that size, then lots of questions go away. What's a good nanoemulsion? Well, this will tell you how to tell a good one from a bad one, right? So if you consume an edible, or if you consume something that has oil or fat, it arrives in your small intestine. After it passes through the stomach, nothing gets absorbed in the stomach. Alcohol does a little bit, but it's kind of an exception. Oils don't. So it gets through your small intestine, through your stomach, into the small intestine. It arrives as kind of like a blob, a drop of oil. And that drop is not water-soluble, right, because it's oil. It can't get through the water to the inner wall of the small intestine. And it has to do that because for a number of reasons that mainly have to do with defenses of your body, the inner surface of your small intestine is lined with something called unstirred aqueous layer. It's basically a mucus layer that's mostly water that is not really moving, and in order to get to the other side of that and get absorbed, you have to be water compatible. Otherwise, you're just not getting there, right? So oil can't do it. It just kind of sits there. Now, in order to bring that oil in, you have lipases and bile salts and phospholipids that are locally generated. They come and start digesting this oil. By digesting, well, when you digest the triglyceride, you clip the glycerin group off and you release the fatty acids. And so you take these fatty acids, release them with lipases, and they self-assemble into something called mixed micelles. Mixed micelles are basically oil droplets. They get phospholipids and bile salts, which are surfactants, biologically generated surfactants. Those end up on the surface, and so now you have these mixed micelle nanodroplets, about 10 to 30 nanometers in size, depending on what's inside. And if you have cannabinoids, those can't get digested because lipases only work on triglycerides. They don't work on other oil-compatible things. But cannabinoids will simply find their way into the interior of these droplets. So now you have a very similar situation to what I showed you before. You have this droplet. It has surfactant on the outside. It's about 10 to 30 nanometers in size. It has oil on the inside, and inside that oil there's your bioactive cannabinoids or coenzyme Q10 or who knows, vitamin D, right? Anything that's oil soluble. Now these can now travel through water because they're small. Now the inside of your small intestine has a structure. It's called villi. So they're kind of protrusion, like finger-like protrusions lining the surface. Now these villi are composed of enterocyte cells. Those are the absorption cells. That's how things go into your bloodstream, through those cells, or into the lymphatic fluid. That's a little bit beyond the scope of this talk, but you could go into the blood or you can go to the lymphatic fluid. These enterocyte cells have microvilli on top of them. So that's these pink things you see there. Those are about 100 nanometers in diameter, and the space between them is 100 nanometers. So in order to get absorbed, you have to fit in between them. That's how you go in as a droplet, right? Now, if your droplet is bigger than 100 nanometers, it just won't fit. It can still probably get absorbed, but the efficiency is lower. So when the droplets are well below that, that's when the absorption really gets intensified. And that's why nanoemulsion droplets should be around 20, 30, 40 nanometers or so, because they fit properly. And importantly, this thing takes a long time. So to make these mixed micelles, it takes about an hour for this process to even get going properly. After about an hour and a half, you have enough of them. Now they can travel, and then they get absorbed. So after maybe a couple hours, this process is really going. And after 3 hours or 4 hours, it gets up to its maximum. And that's why edibles do what they do. You consume an edible, there's nothing for an hour. Then maybe you think you didn't take enough. Maybe you think you need to take a second one. A couple hours later, you learn that it was a big mistake that you took the second one because it was just a delay, but it doesn't mean that it's... So then both doses hit you, and then you're in space somewhere. The beauty of nanoemulsions is that these little droplets, you can just consume them directly. That's what you're doing when you're consuming a nanoemulsion-based beverage. You're consuming a suspension of pre-digested droplets that were simply digested with a proper technology outside of your body. And you don't have to wait for an hour and a half for this thing to happen on its own in your body. That's why the peak is not smeared, the absorption peak is not delayed, the bioavailability is high, because otherwise, by the time this thing is formed, it's in competition with the normal elimination process. That's why if you don't go in, then you go out, right? But the faster it is, the higher the peak intensity, the greater the bioavailability, and also the more predictable it is. The more prescribable, therefore, it is, right? This is some data that we collected with THC samples. So it's worth going through it quickly. The blue line and the red line are basically edibles. 10 milligram dose of THC consumed in the case of this blue line as an oil capsule, and in the case of and the red line also as an oil capsule. The difference is, that the blue line is on a full stomach. The red line is on an empty stomach. So let's talk about the blue line. This is a typical edibles profile. There's nothing for a couple hours. After that, it picks up. After about 3 hours or 3.5 hours or so, it's at its peak. Then it goes out, and there's this really long tail that, I guess, if you consume an edible, you wake up in the morning and maybe it's still there. And maybe you need to go to work, but maybe you shouldn't. The red line is the same, but on an empty stomach. And it's also known that edibles should be consumed with fat or with oil, right? Because that helps bring it in. Well, here's what happens if you don't. So there's this tiny little bump after about an hour and a half, right? And after that, it starts to even that little bump starts to dissipate. So at this point, we allowed people to eat And it turned out that the stuff is still there, it just can't go in. And you get this little second bump at about the same timing as you would from an edible on the full stomach. But interestingly, this is all smeared, and the peak intensities are not particularly high. It was a relatively small dose, 10 milligrams. Now look at the green and the purple line. Same dose as nanoemulsions. Green on an empty stomach, purple on a full stomach. So the green one is basically a glass of wine. You consume it, 10 minutes later you feel it, maybe 15 minutes later you feel it, maybe 40 minutes later or so, it's at the top, then it stays flat for a couple hours, it goes out, and then it's gone. That's basically an alcoholic beverage. Now, alcoholic beverages also depend on whether you ate or not, right? So the purple line is the same on a full stomach. So on the full stomach, it's a little bit delayed, and that's probably because of gastric emptying. Gastric emptying simply means that if you ate something, it sits in your stomach, and then if you consume something else on top of it, it's going to have to wait its turn to empty into the small intestine. So there's like a delay in arriving to where you could be absorbed. But then the intensity is perhaps a little higher. The bioavailability is a bit higher because there are several potential reasons for it, and it's not entirely clear why that is. One of the possible reasons is because oils and fats help you bring cannabinoids into the lymphatic system rather than into the bloodstream. For CBD, it's actually a really good idea to do that because CBD gets destroyed in the liver. So just very briefly, when you go into the bloodstream, that happens when there are no oils co-administered on an empty stomach. You go into the portal vein that takes you straight into the liver. Now, the liver will metabolize the material. If it's CBD, it will deactivate it. But if it's THC, it will make 11-hydroxy-THC from it. So with THC, it's a big question. Where do you want that? Perhaps you want it in your bloodstream so that it can get metabolized and become an even stronger 11-hydroxy-THC, which is actually faster and stronger. But not all of it becomes that, so some of it gets deactivated in the liver. So it's an interesting mechanism. It's kind of left for the future right now, but it's a lever you can pull. But interestingly, it's the other way around compared to the alcohol industry. So an alcoholic beverage on an empty stomach will hit you much harder, right, than on a full stomach. With cannabis, it's not exactly so. It's probably the inverse, with THC at least. Now, this is a very elegant study from the pharmaceutical industry. It's not done with cannabinoids, but it really belongs to the method of delivery rather than the bioactive itself. It just shows you what happens when you administer things as nanoemulsions of different droplet sizes. So at the bottom, these triangles, that's a nanoemulsion with 400 nanometer droplet sizes. So that's really not a nanoemulsion. It's kind of like a crude macroemulsion where oil is somewhat mixed with water. It's basically an edible, a little bit better than an edible. And you see the peak concentration is pretty low. Now, interestingly, once you get under 100 nanometers, so that's, I'm looking at a different screen. I wish I had. I don't have a pointer, do I? Laser? No? I do? Oh, I do. Oh, look at that. Oh, that's a whole other conversation. Yeah, so this is basically an edible. Now, all of this stuff here is under 100 nanometers. And these triangles here, that's about 40. And this is 25. So you can see that once you're under 40, it's diminishing returns. You're pretty much at the top. And if you made it much smaller, it wouldn't really matter. Because once you fit in between these microvilli, well, when you fit, you fit. Then everything gets absorbed properly. Another interesting property of nanoemulsions is that they become translucent, as I mentioned. And this is what happens when you keep processing. It's the same formulation. You just keep going in the process of making it. And it starts out as milky. And then it becomes progressively translucent as the droplet size goes down. Now let's talk about how you can make some of your own without having to be a scientist or an engineer. Our company, Industrial Sonomechanics, offers a complete solution, actually a set of complete solutions you want to make. There are two sides of it. One is ultrasonic equipment, and we offer it at lab, bench, or industrial scale with everything included that you would possibly need to do it. And we offer formulations. They're called nanostabilizers. At this point, we offer two of them. One is nanostabilizer LT. That will lead to liquid translucent nanoemulsions. That's why it's LT. And the other one is LSO, nanostabilizer LSO. With that, you could make powders. Or you could make also liquids if you want, but most people choose to make powders from it. The powders are very convenient to use as powders or to compress into tablets, and then you can make quickly disintegrating tablets that you put in your mouth, and they just fall apart, dissolve in your saliva, and you swallow them. Here we go. A little bit more about each system and the productivities. This is our lab scale system, LSP 600. With this system, you can work with 2 liters at a time, but it's not a production system. It will make enough samples for you to evaluate the technology, maybe make small runs, but it's not something that's going to be producing your product 24/7. The productivity is about 1 liter an hour, which means you can make around 5,000 10-milligram doses of whatever cannabinoid you're working with. The medium system is BSP 1200. It's 5 times faster. You could make 5 liters an hour with this thing. And that's about 5,000 doses, each dose being 10 milligrams of CBD or THC or another bioactive in the form of a nanoemulsion. So 5 liters an hour of that. And this is our largest system, ISP 3600. It's typically used by multi-state manufacturers, so more for CBD production, but large companies also use it for THC. It can make up to about 100,000 nanoemulsified doses per hour, which is about 20 liters of nanoemulsion. Briefly about nanostabilizers. This is nanostabilizer LT. This is what it looks like. And it will lead to a translucent liquid nanoemulsion. Droplet size is approximately 27 nanometers or so. It comes with SOPs. You don't have to invent anything. You don't have to really make any decisions. You just follow simple procedure. But if you want to experiment, there are lots of things that you could do with it. For example, you could use it in ratios that we recommend, or you could change that. So we recommend using 5 parts of nanostabilizer to 1 part of your cannabinoid. The process is very simple. You simply mix the 2. That mixture goes into the ultrasonic system with some water, and then you just push the button that says start and wait for this nanoemulsion to become translucent, or if you have the ability to measure droplet sizes, that's better. Then you know when you're done, but you don't have to really do anything. You just watch the system produce. And I should have mentioned that the BSP 1200 and the ISP 3600 are both 24/7 production systems. They're water-cooled, they don't overheat, they never have to stop. You could just work. They're flow-through, so those are the systems used to actually pump out product. But if you take the 5-to-1 ratio that we recommend and change it, let's say you go to 4-to-1, the droplet size goes up a bit, but the formulation is still translucent. You can see it, and this is in its concentrated form. So once you dose that into water, it becomes completely transparent. If you go to 3-to-1, you're still okay. But if you go below 2.5 or 2-to-1 or so, you can see that the upper edge of the distribution here, so this upper edge here, starts to exceed 200 nanometers. So this is not the median, this is the right tail. And that's a problem because you really should, at the end of the process, filter your nanoemulsion. Filtration is done for a number of reasons, but it's good, if possible, to do sterile filtration. That make sure that the nanoemulsion has absolutely no microorganisms on the other side of it. And you cannot do that if your droplets exceed in size the size of the pores in the sterilizing filter, and that's 220 nanometers. So we recommend that you not go below about 2.5 to 1. But you could go anywhere from 5 to 1 to 3 to 1, and really it's just up to you. It could be economics, it could be that translucency is not that important to you. Who knows why? You have that flexibility. Now let's talk about stability. Stability is an important parameter. It's also going to be probably a recurring theme here. So this is some data we collected with an orange photonics unit. It's a liquid chromatography unit that we use and like. It's good for nanoemulsions. You can see that for a nanoemulsion, that's the blue line, which was in a dark glass container, the stability really doesn't change. We still have some nanoemulsions we made a couple of years ago, and they're exactly where they are. Stability in the sense of CBD in this case, being detectable as CBD, not the droplet stability. The droplet stability of a nanoemulsion is really rock solid, years, if you make it properly. But if you have this nanoemulsion in a clear glass container, it's a little bit different because of UV. So this was sitting in the lab, not in direct sunlight, but in an ambient light. And you can see that after about half a year, the concentration of CBD starts to go down because it gets oxidized. And also it becomes pink because you're forming quinones. Nanostabilizer LSO is the other formulation that we offer, and it leads to powders. It itself is a powder. It will make nanoemulsions with droplets just under 200 nanometers. You can reconstitute it in water and make a beverage, or you could, as I mentioned, make a tablet out of it, convenient. There are many other things you can do with powders. You can, for example, add them to things where water can't go, for example, to chocolate. Mix them right into the chocolate. That really helps because you get the benefits of nanoemulsion in a place where a liquid nanoemulsion based on water couldn't really be, right? And nanostabilizer also is a lot more permissive in terms of concentrations. You can see that you can change concentrations from the recommended 4 to 1 to 3 to 1 to even 2 to 1, and the droplet size doesn't really suffer until you go too low, and then suddenly everything just doesn't function properly. Lastly, I'd like to emphasize that we can also not only enable you to make your own, but we can make these things for you. We do contract manufacturing. Both liquid and powdered nanoemulsions could be made. And there's an additional formulation that we make, and we have samples of this here, so you can test some of these and see if you like them. It's our premium powder with droplets that are much smaller, about 35 nanometers or so. This powder goes completely clear in the liquid and dissolves very quickly. So if you have something like a sugar packet that you'd like to put, especially into cold water, that is a good powder because it's very quick. And with this, I thank you for your attention. I'll take questions.